If our now next question is question number 37, case study 2 of 4 marks each. And we are given a tank as shown in the figure formed using a combination of a cylinder and a cone. So this is the shape of the tank because it offers a better drainage as compared to a flat bottomed tank. It's obviously to clean at the bottom, it's easy because it's a cone at the bottom. And okay, now it's given that a tap is connected to such a tank whose conical part is full of water. So this is the water is only in the conical part. So let's say this is the conical part of the tank. So water is only in the conical part. Let's say R, small r with the radius, h be the height, and L be the slant height. Now water is dripping out from a tap at the bottom at the uniform rate of, so water is dripping out from the bottom using a tap. So there's a tap at the bottom and the semi-vertical angle. So semi-vertical angle, this is the vertical and the semi-vertical angle is 45 degree. Okay, once it's 45 degrees, so in this right angle, the triangle, that is this one. So we have this right angle triangle and this is 90 degrees. So tan 45 is equal to this is the hypotenuse, this is the perpendicular, and this is the base, which is P by B tan 45 is 1. Perpendicular is R and base is H. So this gives us H is equal to R. Let's keep this information with us. Okay, now we have to find the volume of water in the tank in terms of radius R. So volume of water in the tank in terms of radius R, volume of the cone is pi R squared H and H is equal to R. So it's pi R squared into R and this is the volume of the tank in terms of R. First one, and now we have to find the rate of change of radius at an instant when R is equal to 2 root 2. So rate of change of radius, and we missed the information that was given to us. It's water is dipping at the uniform rate, so the water is coming out. So water means the volume of the water is coming out at the rate of it's coming out, so it's negative 2 emptying the tank, so it's negative 2 centimeter cube per second, and volume of the tank is 1 by 3 pi r cube, that is minus 2 centimeter cube per second. And differentiating this with respect to r gives us 1 by 3 is constant. Differentiation of r cube with respect to t is 3r square into dr by dt, which is equal to minus 2 centimeter cube per second. Okay, now 3 and 3 gets cancelled. And rate of change of radius is equal to minus t upon pi r squared. This is centimeter per second. Now, we have to find the rate of change of radius when radius is 2 root 2. So this gives us minus 2 upon pi 2 root 2 the whole square centimeter per second. And this is minus 2 upon pi into 2 square is 4. Root 2 square is 2. So this gets cancelled. And now this is minus 1 upon 4 pi centimeter per second. So this is the rate of change of radius when r is equal to 2. Okay, so we have got the rate of change of radius, and now we have to find the rate at which the wet surface. So the wet surface would be the curved surface, and we have to find the rate at which the wet surface of the conical tank is decreasing. So when it's full, the complete uh, the curved surface area is wet, but when the water is dipping out, the wet surface is decreasing. And let's say the wet surface area is, let's say it's a curved surface area, so it's pi r, and this is the third. So we are doing the part A of the third. So the wet surface area is curved surface area, which is equal to pi r l, and we have to find the rate at which it's decreasing. So L, and we know that L square is equal to h square plus r square. H and r are equal. We have proved that in the beginning. So L square it can be written as, so instead of h, I can write r square. So L square is equal to 2r square and L is equal to root 2r. So this gives me pi into r into root 2 into r, and the curved surface area is pi, or let me write it as root 2 into pi into r square. Okay, now let's find the rate at which the curved surface area is decreasing. So this is differentiation with respect to d, and r square is 2r into dr by dt. Okay, we have the rate of, so this curved surface area has to be decreased when radius is 2 root 2, it's given. So when radius is 2 root 2, we have got that rate of change of radius with respect to time when radius is 2 root 2 is minus 1 by 4 pi. So this is now root 2 pi into 2 into r is 2 root 2, and this is minus 1 upon 4 pi. We have already calculated is minus 1 upon 4 pi. Okay, now this is, so 2 into 2 is 4, so this gets cancelled with this, and root 2 into pi gets cancelled with pi. Root 2 into 2 is 2, so this is negative 2 centimeter square per second. So this is the rate of change of decrease of the curved surface area, which is negative 2 centimeter square per second. And okay, so now we have to, so this is done. Okay, we can also do the odd option part. We define the rate of change of height at an instant when slant height is 4 centimeter. So this is the optional part, that is the third. Now relation between height and radius is this. It's given L is 4, so this is 4 square. H and R are equal, so this is R square plus R square, as height and radius are equal. Sine vertical angle being 45 degrees, so this gives us 16 is equal to 2R square. R square is equal to 8, and R is equal to 2 root. Now we know that L is equal to H, sorry, H is equal to R, and we have to find the rate of decrease of the height. So this is, sorry, this is H is equal to R, and if we differentiate this with respect to d, dH by dt is equal to dr by dt, and because we have to find it at when radius is equal to 2, so this is dH by dt when radius is equal to 2 root 2, and this is equal to dr by dt when r is equal to 2 root 2. And we have already calculated this rate of change of, so this is equal to this, and this we have already calculated. Dr by dt when r radius is equal to 2 root 2 is minus 1 by 4 pi, so this is minus 1 by 4 pi centimeter per second as well. Okay, and this solves our question number 37. Let's move on to the last one, the case study 3.